the question is implement malloc and free on top of the built-in malloc. So like you don't have to implement malloc from scratch. You're allowed to just call regular malloc and regular free, but I want you to implement a new function for me called aligned malloc, where it takes in both the number of bytes that you want and some desired allocation. Actually, let's call that alignment. Some desired allocation. Some desired alignment of that allocation. So by default, most systems these days will return to you, if you just call malloc, they'll return to you something that is probably aligned to either 8 or 16 bytes. Like just kind of by default, that's what they're going to return to you. But if you have the need for it to be aligned to something more specific than that, or if you're on a system that doesn't have that sort of guarantee, I want you to provide an implementation. So you're going to write this code to implement this aligned malloc function. So that's the prompt here. And what I think that the easiest thing to identify is that regularly when we call malloc, we get back a block of memory and we get a pointer to the beginning of that block of memory. And if we ask for 100 bytes, then the block of memory is going to be at least 100 bytes long. If this starting address is, let's say, a multiple of 4, let's say. Now let's go even crazier than that. Let's say it's a multiple of 10 is the default alignment. It happens to the address that you happen to get back when you called malloc happened to give you an address that was at a multiple of 10 offset. And the alignment requirement that someone else asked for is that it be a multiple of, let's say, 15. Kind of silly numbers, but once again, this aligned malloc function needs to work for any of them. So what we get when we call malloc is this address, but what we need to return from aligned malloc is some multiple of 15. Maybe we return 15, maybe we return 30, maybe we return 45. It doesn't really matter what it is that we're returning as long as it's a multiple of whatever that alignment requirement is. But if someone asked for 100 bytes and we called basic malloc for 100 bytes and then started doing something like returning an offset into that 100 bytes, now we no longer have 100 bytes left. We only are giving back a pointer to 95 bytes. So what we need to do is we need to over allocate memory so that we have space to return one of these, presumably the first one, but at least one of these future offsets. And we're running low on time, so I'm going to make this slightly less interactive and just jump to some code that I had written. And this is kind of my initial instinct for what I would implement to what code I would write to implement aligned malloc and free. This should be aligned free, not aligned free. So the first thing what I'm going to do is I'm going to call malloc to actually get memory. Once again, the purpose of this question is saying that you are allowed to just call malloc, but the result of your function needs to be aligned. So I'm going to call malloc and I'm going to pass in the original size that the client asked for, and I'm going to over allocate. I'm going to over allocate by the amount of the alignment, and I'm also going to over allocate by a couple more bytes. And I'm going to get into why I over allocated by more bytes in a second. So I'm gonna allocate more memory than the client specifically asked for. And I'm gonna save this in this local variable RV, return value. What I'm also going to do is increment return value by the size of a uint32. So I'm going to increment it by 4 bytes. Because what I'm going to do is store the required offset in those 4 bytes. So let me get to that in a second. So we allocated memory, we stored it in RV, we incremented RV by 4, and now we need to figure out how far off are we? If someone asked for something to be a multiple of 15, and what we are is at 10, then we need to increment, or we need to return a pointer that is 5 bytes further than what we currently have. So we need to do a little bit of math to figure out how much we need to shift it. I'm going to call that our offset. And then we're going to increment our return value again by that offset. And then ultimately, we're going to return that return value. So once again, we allocated memory, we incremented it by 4, we incremented it by however much is necessary to make the alignment requirement that the client asked for, and then we're going to return that pointer. If that was all we did, so I mean, now we've technically met the requirements of an aligned malloc. Whereas if someone asked for an allocation that is aligned, we are giving them back an allocation that is aligned. But how do we free it? We called malloc initially to allocate this memory. We're going to need to call free later on to free it. And whenever you call free, you need to pass in the same address that malloc returned to you. But if we return this RV to the caller, this RV is not the original thing that was malloc. And then the caller is going to pass that back here when they call free. That means this pointer cannot be passed here to free. This pointer would be an illegal input to free because it is not originally a pointer that malloc returned. So what we need to be able to do is within free, within our free function, we need to figure out how much did we shift over that address? How much did we shift it over? And then we need to unshift it. We need to pass into free whatever the original pointer was. And this ends up being a non-trivial thing to do, because within free, it's very difficult to figure out, well, what do we go back to? We don't know what the alignment request was within free, because free just contains the pointer. The alignment requirement was only specified in the malloc. So we don't know how many bytes to subtract. We don't know how many bytes to subtract within free, just given that pointer. So what we need to do is store this offset at some known place so that we can look it up again later. And in my solution, what I do is I take the return value that I'm ultimately going to return, and I subtract 4 bytes from it and store that pointer into this storage local variable. And then at that location, I store the offset, as well as the fact that I changed it by 4 as well, but I store that offset at this location. So conceptually, I allocated initially, let's use the same nomenclature. I allocated size bytes, I allocated alignment, and I allocated 4. That's what was being allocated up here. And now what I'm doing is I am going to return some address like right here, such that I still have size bytes remaining. And then right here in this space, I am going to store how much I had to shift. So how, oops, let's do it in different colors so it's not just all the same thing. how much did I have to shift to make that size, to make this pointer correctly aligned? I'm going to store that data right here. And then down here in my free function, I take my pointer that was passed in, I subtract 4 bytes from it, so that now I have the same memory address I had up here when I was storing it. And now I can simply dereference that value. So this offset here ends up being the exact same number that I stored up here, cross right there. And then I can do my pointer, subtract the offset, and then free that original pointer that was originally returned from malloc up above. So the key thing here is I needed to over allocate memory, and then I needed to save somewhere how much I had to shift in order to make that alignment requirement. And then I used that saved offset in free to unshift it. And just to reemphasize, this question was not asking us to implement malloc. This question was saying that we could use the standard system malloc and build our implementation on top of it.
Hey, Glenn.
Yep.
I was just trying to understand the line before return in the aligned malloc. We store the offset into a specific location. I was trying to see offset plus you are doing size of uint32, which is 4 bytes.
Yeah. So remember what I'm going to return. What I'm going to return from this function is RV, and what I need to get back to is whatever malloc returns. And so I incremented RV here, and I incremented RV here. So I need to store those 2 pieces of information here so that I can subtract the same thing down here.
Okay, so whatever offset you have moved the RV forward, that is stored in the storage. Makes sense.
Yeah. And technically speaking, I could have not stored this there because it's well known that I'm using 4 bytes. But then I would have had to subtract the 4 bytes down there. So I either needed to add it up here or subtract it down there. And I thought it was easier to read code putting it up there.
Yeah, makes sense.
Note that this code is slightly inefficient in that I, in many cases, waste more memory than I actually needed to waste. For instance,
so one thing like we could always do is alignment -1, right? We don't need to do over allocation of alignment itself. So
that is exactly what I was.
Oh, go ahead. No, if alignment is off, you always have to maximum allocation should be alignment -1.
So you're right in that if the alignment is whatever we get back from malloc, if it's not aligned, then we're already going to need to increment it here. So we're already going to have at least 1, if not multiple, free bytes available to us to write stuff into.
No, that's fine. I'm not pointing to that. I mean, just one first level optimize, not optimized, but at least you see in the malloc we are doing size plus alignment plus size of for the offset. I mean 4 bytes extra for the offset, right?
Yep.
But the alignment alignment allocation would be alignment -1. That should be good enough in all the cases, right? We don't need to. So we'll say 1 byte there. I mean, we would always still need offset to be stored. Even at offset also.
Oh yeah. Oh, I see. Yes. Past the end of here, subtract not 10. Sorry, subtract 1.
Yeah.
Yes, you're absolutely right. Yeah. I would have to change my code though. It was right here. This line. If you notice, if I allocate something that's perfectly aligned, the result of this isn't 0. The result of it is alignment. Like if it's perfectly aligned, it is alignment -0. So with the particular code I have here, we shift over even when we
Okay.
didn't need to.
Yeah,
So
makes sense.
you're right that we could subtract 1 here, and that would definitely save us memory, or even a small amount. It would be more efficient in that sense. But I would need to fix this code so that we, in the case of perfect alignment to begin with, we don't do any shifting.
Yeah.
Any other thoughts or comments from other folks?
Hi, Glenn. Could you quickly go through one example of the numbers here?
Sure. So someone might ask for an allocation of size 100, and they might ask for an alignment of size 9. So we would then allocate, we would call malloc with a total of 113 bytes. So we would get a allocation of size 113 bytes, and then we would get some address back from malloc, 0x whatever it happens to be. We get some sort of address back. And then what we need to do is first increment this address by 4. So if it starts off, let me do it kind of to the side here. And let me actually use a smaller number. Let's do something like that, the number 3. 3 is obviously not a multiple of 9, so we need to do some sort of alignment at least. So next we're going to increment RV by 4. So then we're going to get the number 7 here. Then we're going to say alignment of 9, RV, at least the least significant bit is 3. Or actually, I suppose in this case, I chose a number that's too small. I assumed in my code that we were never going to receive numbers that close to 0, as you don't in practice. But in any case, 3 mod 9 is going to be 3. So now we're going to do 9 minus 3. So we have 6 is our offset. So we are going to increment this by 6 again. So 7 plus 6, and rather than trying to do it in hex, let's just say we get to the address 13. Down here we have let's see here. We have 13 minus 4. So at location 9, we're going to write 7 plus 4, we're going to write 11. Sorry, for some reason my numbers don't make any sense anymore. We're going to write, so 4 plus 6, sorry, not 11, 10. That's why we had an offset of 6, plus we have the size of a uint32. So our storage is total offset we're going to write at location 9 is 10, and then we're going to return 13. Down here, the address 13 is passed in. We are going to do 13 minus 4. So at location at address 9, we are going to dereference whatever is at 9, and we wrote 10 up above. So we get 10 here, and we're going to take the pointer, which was 13, and subtract 10, which gets us 3, and we're going to free the number 3, which is the same address up here that we originally got returned from malloc.
Thank you.
Yeah, sorry that was a little bit of squiggliness, but maybe hopefully that was helpful.